All right, last two major reactions. Double replacement will be our focus because there's a tremendous amount of homework that's going to be covering over it. We said watch out for it in particular because it does have two things before, two things after. And we see that here. We also see that both partners are trading. If both partners are trading, they're going to end up with both partners having new partners in the end. So it's kind of like the 60s and swinging, or maybe the TV show called Wife Swap. But regardless of the analogy, you have to have a person with a partner, and then a new person with a new partner, a new person with a new partner. So that idea of AZ plus a BX, and notice now we switch and we get a AX and a BZ. But in order for any of this to happen, we have to have somebody with a positive, somebody with a negative, somebody with a positive, somebody with a negative, and then switch the positives and the negatives. If the charges are different, that's going to require some chemical reaction balancing as a result. But you have to have two elements to make compounds, and if you don't, it's probably going to be single replacement. If it has oxygen, CO2, and water, it's probably going to be combustion specifically. So look out for two compounds making two different compounds. What we're also looking for is who stays water soluble and who doesn't. That's a tremendous amount of homework and matching sections specifically. Water soluble just means when you add it to water, it disappears. It becomes transparent, no different than salt or sugar being stirred into water. Insoluble means you can stir it for as long as you want. It's just going to sit there and make a cloudy or a suspension, or it's going to settle to the bottom. So our job is to use a solubility table that we get on the exam to know who is water soluble and who isn't. So as we look here, what we're going to see is we ended up with a solid. So this is something that will turn, a color, turn a thickness. It'll be like a white pasty or yellow pasty kind of semi-solid. When you mix these two together, immediately forms, and we saw that back in our early experiments when we dropped things into test tubes and they turn cloudy. So our job is when does this happen and when does it not? Because if it doesn't happen, then it's no reaction. So here's the solubility table coming up. In the solubility table, again, what we're looking at is, do we have some of these magic ions, like sodium, potassium, ammonia, like acetate or nitrate, that stay water soluble? If so, it's going to stay clear, it's going to stay transparent. If it's not, then we have some exceptions to worry about, and that's what makes it a little bit difficult. So let's go back to this slide I skipped over. The ability to be soluble means you dissociate, means when your crystals are sprinkled into water, water uses its polarity to break apart those positive negative ions through an ion dipole interaction that we'll see in one of our later chapters, chapter 15, when we cover solutions. But suffice it to say, if it disappears in the water, that really means dissociates into water. It means it breaks apart into water, into this homogeneous solution that looks maybe like water in the end. Maybe it has a color, maybe it doesn't. So this table that I mentioned shows us when that happens. It shows us that as we look at the metals or the polyatomic ions, we can predict when to see a precipitate and when not. My hope is that you look at this chart and you realize these magic five. These magic five are sodium, potassium, ammonium, acetate, and nitrate. And if we have those, we have solubility every time. We have water solubility every time. So notice they're mentioned down here as exceptions because those two are going to break the rules and be a reason for solubility to exist. So the important feature here is there is no exceptions. If there's no exceptions, that means we can say that these are water soluble every time we see them. These are safe. And if they're water soluble, we can also say these are spectator ions because they're going to watch this reaction happen. They're not going to participate. And notice they just make kind of a diagonal. These guys are these guys. It's just reminding you that, hey, they're never going to be insoluble. They're always going to be soluble. That tells us that if you're insoluble in water, so that's these guys over here, if you're water insoluble, that means you're going to be a precipitate. And they remind you that precipitates will never be the magic 5. So there's several of those listed again to remind you of that. But really what we have is those in the exceptions. Those are the ones to watch out for precipitates, for water insoluble. And most things that are water insoluble happen to deal with things like lead, things like silver, mercury, calciums, bariums, although there are some exceptions with the hydroxides of calciums and bariums. So be careful with these because they have exceptions, and be careful with these because they have exceptions. But one thing we can take for granted is if it has one of those magic 5, we're safe. We know it's water soluble, we know it's a spectator every time. So I can't stress enough, you can answer a tremendous amount of homework by looking for these magic 5 because they're always soluble in water, they're always spectator ions, they're always going to watch. They're not going to precipitate, which is very similar to participate in the reaction. They're going to be sitting on the bench. So we talked about the rules on how to recognize them. We just need to start to look for those magic 5. And notice in this reaction here, we start to see that when we mix lead and nitrate together, nitrate is one of the magic 5. If we take sodium and iodide, mix it together into water, sodium is one of those magic 5. So sodium and nitrate really don't do anything. They just bring lead to the party. They just bring iodide to the party so that lead iodide can form as a kind of yellow precipitate in the end. So notice in the net ionic equation, we don't use those at all because they were part of this magic 5. These are like the designated drivers. They're the ones that go to the party knowing that they're not going to have fun, that they're going to not be the party animals. They're going to be the ones sitting on the bench waiting for the party to be over. So watch out for those because oftentimes scientists use those because they know that sodium, potassium, group 1 kinds of metals are very safe. They know that ammonium and nitrate ions very safe. They know that ions of acetate very safe, never make precipitates. So they're perfect partners to mix together because we know that the partners to them are the ones we have to watch out for. So let's try an example. We have sodium sulfate and we combine it with barium chloride. How do we know what happens? Well, let's look at the ions first. When we put barium chloride into solution, we know chloride is, if you look at your solubility table, we know it does have exceptions. So if we were to look at the solubility table, we'd know that watch out for silver, lead, and mercury. But as long as we're not with silver, lead, or mercury, halides are just fine. And here we have barium with chloride, so we're perfectly water soluble. That means AQ. Sodium is one of the magic 5. There's no exceptions to why sodium would be ever insoluble. It's always soluble. And because it's one of the magic 5, we know that it's aqueous. So we said more than anything, watch out for the magic 5 and notice of the 4 pieces, they use one of those, and that's very common. It's even more common to use one in each beaker to be even safer yet. There isn't any rules on barium. There is a portion on sulfate, but what they say about sulfate is to watch out for things like lead, calcium, and barium. These tend to make sulfate precipitates, and guess who is in the other beaker? And the other beaker is the long-lost friend from high school. And if they get together at this beaker party, when they're mixed together, that can lead to a precipitate in this case. So sulfate is usually well behaved, except for these three, and turns out this one's coming into the beaker very soon when we mix them together. So when we pour them together, they have a chance to mingle at this party. They have a chance to, kind of dance around together. So when sodium dances around with now chloride, which is not the partner it came with, but another partner at the party, this just makes salt. And salt in this case, because of sodium, that's the magic 5. And that's going to make it perfectly water soluble. However, barium, for the first time in a long time, is going to meet up with sulfate. And when we get barium sulfate, we're going to look at sulfates on the solubility table and see that sulfate has exceptions of lead, calcium, and barium in particular. And because of barium, this is going to be your solid. So salt's going to be aqueous, but barium sulfate's going to be your solid. And this one's going to turn this beaker a color, in this case, white. So again, NaCl, perfectly water soluble. Plenty of salt in the ocean that's perfectly water soluble. Only with lead, silver, or mercury is this an issue, and that's not the case. And the other beaker is barium, and barium is perfectly happy with chlorides. Barium is not perfectly happy, though, with sulfates. Sulfates of calcium, barium, and lead, we said, and strontium is also in the mix, too. It's those group 2 sulfates that we saw in those test tubes early in the semester. Carbonates, same way. Phosphates, same way. So who really matters for the reaction? Who matters is definitely not sodium, because sodium just brought sulfate to this beaker party. And definitely not chloride, because chloride just brought barium to this party. But when barium was in solution because of chloride, and when sulfate was in solution because of sodium, they had the ability to meet for the first time in a long time and now make the white precipitate barium sulfate. So recognizing these as not the magic 5, but as an exception to the sulfates, which are typically water soluble, barium just happens to be one of the 4 that make an insoluble precipitate of sulfates. Turns out acid-base reactions are the exact same way. They work in a double replacement kind of reaction. So what's useful about this typical kind of reaction is look for the same kinds of things. Look for 2 partners with 2 partners, both switching. But in this case, it's a little bit different because we're not looking for some kind of precipitate. Instead, what we're looking for is acid, H's, looking for OH's, which are bases. If acids and bases get together, H's and OH's can make water. So what we're looking for here is the formation of water, which is difficult because you're in a solution of water already. But typically what happens, though, is you also get a lot of heat. So these reactions warm up when they start trading partners, and you can feel that outside the test tube or outside the beaker. So in an acid-base neutralization reaction, which is just a fancy name for acid-base double replacement, we have this same pattern that we said to watch out for. You have AZ, you have BX, and now notice we have BZ, and if we write water as HOH, to make it a little bit easier to see, now we can see that here's the A, and here's the X. Consequently, you can also see that A in this case stands for acid, and B in this case stands for base. And when the acid and base come together, the H specifically and the OH specifically, that makes water HOH. So sometimes to balance these equations, it's a little bit easier to write it as HOH, because then you see that you don't have to count H and OH separately for their H's. This hydroxide here, you can keep as a group because it's still hydroxide in the end. So when you balance these equations, my preference is to draw HOH instead of water to make those double replacements a little bit more visible and a little bit easier to balance as a result. In the end, who did it matter to bring H to the party? Well, whoever brings acid to the party. Kind of sounds funny when you say it out loud. But whoever brings acid to the party is kind of irrelevant. Whether it's chloride or nitrate or acetate, any of those would have been perfectly fine because there's no silver leads or mercuries around to deal with those chlorides. And irregardless of sodium, sodium's the magic 5. That's a perfect base because no matter, it's going to not precipitate or interfere with the reaction in any kind of way because it's always going to be water soluble in a spectator ion as a result. So the spectator ions are missing. Those are sodiums and chlorides. The water formation, the liquid formation, is much like the precipitate formation from our more traditional double replacement reactions that we saw earlier. As we wrap up this chapter, we also want to revisit the idea of combustion. Combustion is very specific, though. If you don't have O2, CO2, and water, it's not combustion, period, in our textbook and in our homework and our test. So if you don't see O2 gas, if you don't see CO2 and water, and it's possible that these two may be flipped, front to back or right side up, doesn't matter who's first as a product or who's second. What matters is if you don't have O2, CO2, and water, it's not going to be combustion, so you have 4 choices left. And if you see 4, compound-looking things, or 4, 2 things before, 2 things after, you definitely know it's not combination or decomposition from the get-go. They're only going to have 1 thing in front or 1 thing after. So really pay attention to if you have 2 things in front, 2 things after, do you have O2, CO2, and water? If so, combustion. If not, is it single or double replacement? Well, if that were the case, look to see if they're partnered up. If they're partnered up before and after, that could be a double replacement. But notice in this case, we have oxygen that doesn't have a partner. So it wouldn't fit either single or double replacement because you have 2 partners over here, you have a partner on the reactants, but you do have one that doesn't have any partner, but you never end up with a different kind of single in the end. So even if you get confused, this one doesn't fit either single replacement or double replacement because oxygen never has a partner. So last thing we'll do is kind of come full circle and say, what kind of reaction is it? Let's go through our checklist. Does it have a single reactant? No. If it doesn't, it's not decomposition. Does it have a single product? No. If it doesn't, it can't be combination. Does it have O2 gives CO2 and water? No, it can't be combustion. So most times students worry about this group of 4, having 2 things before, 2 things after, but we already know that of that it can't be O2, CO2, and water because it's not. Doesn't match at all. So then we look at it, we see that K has a partner with Br. Cl is by itself. It happens to be diatomic, but it's still by itself, no metal partner. Here we see potassium with a different partner, and then bromine by itself. Even though it's diatomic, that's just because of its valence electrons. So notice these guys are singles. Those are like the bachelorettes and the bachelors. They're by themselves before and after. That tells us single replacement because they had no partner before and had no partner after. We'd need another metal in this reaction to be double replacement. We'd have to change it completely to make it combustion. And we'd have to lose a product or lose a reaction to be combination or decomposition. This also kind of points out that what we also see is a single replacement of halogens. It fits this pattern that we said watch out for of, and I think in this case it's reverse, but here's a BX and an A, and we get an AX and a B. So it's that same kind of idea, but notice it's a little different because the partner, the negative partner, is the one that switched. The spectator ion was actually the potassium all along. So it's the one that stayed married the entire time. It's just changing its partners. So no longer are we using an activity series for metals, we're actually using an activity series for halogens, and it works just like the periodic table works. If you're married to bromine first, would you want to marry up to chlorine in your second marriage? And the answer is yes, because you want to marry up. So you can also have activity series with halogens. We just don't really need a table for that because it shows us that on the periodic table. So be mindful of activity series. You're going to get that on the test. Be mindful of the solubility table. You're going to be using on the test. We're going to have lots of exams, or at least lots of experiments before the exam to help us practice all these ideas and get better at them. See you next time.